Refractory ceramics, a material that withstands the extreme heat of furnaces and rockets. This is detailed engineering. Today we're going to dive into a world of extreme temperatures where ordinary materials would simply melt or evaporate. We're talking about refractory ceramics, the true unsung heroes that allow industry to function and make space exploration a reality. Have you ever stopped to think about how it's possible to melt metals at over 1,500 degrees Celsius? Or how a rocket can pass through the atmosphere without disintegrating in flames? The answer lies in these incredible materials. But what exactly are refractory ceramics? Imagine a material that not only withstands temperatures that would turn steel into liquid, but also maintains its mechanical and structural properties under that hellish heat. That's exactly what they do. They are the backbone of industrial furnaces, chemical reactors, and even the heat shields that protect our astronauts. Without them, much of our industrial civilization simply wouldn't exist. They are the final barrier between destructive heat and structural integrity, ensuring that essential processes can take place safely and efficiently. Now the big question: how do these materials achieve this feat? What makes them so special, able to withstand conditions that would disintegrate most other materials? The answer lies deeply rooted in their atomic structure and the chemical bonds that make them up. This is where materials engineering meets physics and chemistry to create true thermal superheroes. Unlike metals, which are characterized by metallic bonds, where electrons are shared in a cloud of free electrons, refractory ceramics are formed by ionic bonds and/or covalent bonds. Think, for example, of alumina, silica, or magnesia, which are fundamental components of many refractory ceramics. In these compounds, the atoms are strongly bonded. In ionic bonds, like in magnesite, there is a transfer of electrons, creating positive and negative ions, which are strongly attracted to each other, forming a rigid and ordered crystalline structure. In covalent bonds like in silica, the atoms share electrons in a very specific way, creating directional and extremely strong bonds. But why are these bonds stronger than metallic ones when it comes to heat? The energy required to break an ionic or covalent bond is much greater than the energy needed to disrupt the electron cloud of a metal. In a metal, increasing the temperature causes the atoms to vibrate more intensely, weakening the bonds and allowing the atomic planes to slide over each other, which leads to loss of strength and eventually to melting. In ceramics, however, the rigidity of ionic and covalent bonds keeps the atoms firmly in place, even under intense vibrations caused by heat. It's like comparing a chain of loose links, which is like metal, with a welded lattice structure, which is like ceramics. The lattice requires much more energy to be broken apart. This high bonding energy is the first and most fundamental secret of the strength of ceramics. Now, directly related to the strength of chemical bonds is the ability of ceramics to withstand extremely high temperatures without melting. Alumina, for example, has a melting point of about 2072 degrees Celsius. And magnesia is even more impressive, melting at around 2800 degrees Celsius. To put this in perspective, steel, a material we consider robust, melts at around 1500 degrees Celsius. And why are these melting points so high? Because the thermal energy required to overcome the strength of ionic and covalent bonds and disrupt the crystalline structure is immense. A colossal amount of energy must be supplied for the atoms to break away from their fixed positions in the crystal lattice and begin to move freely, which characterizes the liquid state. This thermal instability means that even in environments where the metal has already turned into bubbling liquid, the refractory ceramic remains solid and structurally intact, maintaining its shape and function. Another crucial property of refractory ceramics is their low thermal conductivity. To measure thermal conductivity, we use the unit of watts per meter Kelvin. Metals like copper have 400 watts per meter Kelvin, and aluminum has about 200 watts per meter Kelvin, and they end up being excellent conductors of heat. Refractory ceramics, on the other hand, have much lower values, usually between 0.5 and 5 watts per meter Kelvin. But how does this happen? The propagation of heat in solids mainly occurs through two mechanisms: the vibration of the atomic lattice, or phonons, and the movement of free electrons. In metals, the abundance of free electrons allows for a very efficient transfer of thermal energy. However, in ceramics, as we have already mentioned, there are no free electrons. The transfer of heat depends almost exclusively on the propagation of quantized vibrations of atoms in the crystal lattice. The complex and often disordered crystal structure of ceramics, with its defects and impurities, whether intentional or not, acts as a barrier to the efficient propagation of these phonons. The atomic vibrations encounter many obstacles and are scattered, making it difficult for energy to be quickly transferred from one end of the material to the other. This ability to disperse thermal energy is essential to protect the exterior of a furnace or the structure of a rocket from internal or external heat. Another very important point is expansion. Imagine a material that, when heated, expands very quickly. If it is confined, or if different parts of it heat up at different rates, the internal stresses can be so great that it simply cracks. Refractory ceramics, on the other hand, have a low coefficient of thermal expansion. This means that they expand and contract very little with temperature changes. And why is this so important? In high-temperature environments, where there are heating and cooling cycles, a material with high thermal expansion would constantly be under stress, leading to fatigue and structural failure. The low thermal expansion of refractory ceramics minimizes these stresses, allowing them to maintain their structural integrity even under severe thermal shocks. This property is crucial for the longevity of furnaces and for the safety of aerospace components that face abrupt temperature changes. Another important factor is the porous structure of ceramics. And for some applications, the low thermal conductivity of dense ceramics is still not enough. That's where insulating refractory ceramics come in, which incorporate a porous structure. But how does that help? Air or any gas is an excellent thermal insulator, making it have a much lower thermal conductivity than most solids. By creating a structure with pores, whether interconnected or isolated, the air gets trapped inside the material. This trapped air acts as an additional barrier to heat transfer, reducing the material's overall thermal conductivity. It's like wearing a down jacket. It's not the feathers themselves that keep you warm, but the air they trap. The porosity is carefully controlled during the manufacturing process to optimize this insulating property, creating lightweight materials that are extremely effective at retaining heat. And what are the types of refractory ceramics? Based on their composition and properties, refractory ceramics are classified into several types, each one optimized for a specific application. We have silica ceramics, which are economical and used in furnaces for glass manufacturing, and alumina ceramics, which offer excellent mechanical and thermal resistance. And magnesia ceramics, ideal for basic and extremely high temperature environments, such as cement kilns. And silicon carbide ceramics, which combine high resistance to thermal shock and good thermal conductivity for certain applications. In addition, we can divide them into dense refractories, which are structural and resistant to corrosion, and insulating refractories, which are more porous and focused on reducing heat loss. And where can we find these amazing materials in action? Virtually everywhere in heavy industry. In the steel industry, they line the blast furnaces and ladles, withstanding molten metal at over 1,600 degrees Celsius. In the glass industry, they form the melting tanks where sand turns into liquid glass. In cement production, the rotary kilns that operate at extremely high temperatures rely on refractory linings to function. And it doesn't stop there, because oil refineries, waste incinerators, ceramic kilns, and even home fireplaces use some form of refractory ceramics. Your brick barbecue or wood-burning stove needs to have refractory bricks, so the entire structure doesn't crack when exposed to direct fire. But refractory ceramics aren't confined to just the earth. They're absolutely essential for space exploration. Have you ever wondered how a space shuttle or a space capsule can re-enter Earth's atmosphere without turning into a ball of fire? The answer lies in the heat shields made from advanced refractory ceramics. During re-entry, friction with the atmosphere generates temperatures that can exceed 1,650 degrees Celsius. Materials like the high-purity silica tiles that cover a space shuttle are designed to withstand this extreme heat, dissipating it and protecting the spacecraft's internal structure. And more importantly, the astronauts. In rockets, exhaust nozzles and critical components are also made of refractory ceramics or ceramic composites, ensuring that the engine can operate at extremely high temperatures without failing. It's materials engineering at its limit, allowing humanity to explore the cosmos. If you've made it this far and enjoyed the video, make sure to subscribe if you haven't already, leave a like, and turn on the notification bell. And if you find our content interesting, consider becoming a member to help us keep producing content here on the platform and get mentioned in our videos. If you've made it this far, I invite you to take a look at the courses we recommend. So, point your phone at this QR code or click the link in the description about our courses. There, you'll find courses on Excel, 3D modeling, AutoCAD, public speaking, and many others. These are courses selected by us here on the channel, and we can vouch for their quality. And if you want to build your online presence, start recording videos for social media. In this QR code here, we've selected the equipment we use here in our studios. And you, have you ever stopped to think about the importance of these materials? Do you know any other fascinating applications for refractory ceramics? Leave your comment down below, share your ideas, and let's keep this conversation going. Over here, there are 2 interesting videos you need to watch to expand your knowledge and feed your curiosity. To support us, like, subscribe, turn on notifications, and consider becoming a channel member. Thanks, engineering enthusiasts. Take care, and I'll see you in the next video.